post both this. This one's already posted on Uranus, and actually, let me share that with you. There we go. So this one's already posted. So the other one that I do want to post is the Kuiper Belt objects. I almost think that the Kuiper Belt objects are more important than this stuff. And I'll tell you why. Is because, well, I'm torn. But anyway, the reason I think the Kuiper Belt objects are more important and the asteroids are more important is because if I'm talking about an exoplanetary system, if I'm talking about how a planet gets its water, how the planet gets its structure, etc., I'm going to look at the Kuiper Belt objects. Those are the things that if I'm going to check and see if the model of planetesimal planetary formation is correct, I'm going to look at Kuiper Belt objects. If I want to check and see the junk that the solar system was made of 4-point-something billion years ago, I'm going to check the Kuiper Belt objects. So that's, and I'm going to check comets, and I'm going to check asteroids. That's the big thing. Maybe more important than these ice giants. So I'm going to blast through these guys really quick. There's going to be a few things that you need to know on test. Most notably that both Uranus and Neptune are made of methane for the most part. Hydrogen, and it's again a reducing atmosphere. It's made out of hydrogen, methane, a little bit of helium, quite a bit of pneumonia. If you've ever, and by the way, if you've ever smelled a cat box, then you have indeed smelled Uranus and Neptune. Sorry, I couldn't resist that one. So that's pretty much that's it. And they haven't been visited very much. Only one spacecraft has visited both these planets, and that would be Voyager 2. So here's the data for Uranus. 19.49 blah blah blah. Okay, it's Monday. 19 AUs for the average distance to the sun. 20 if you're talking about max, and 18 if you're talking about min. It's almost a perfect circle. The average orbital speed, not that important, but the orbital period of 84 years is important, because if you look on the internet, and I encourage you to do that, find out the year that Uranus was discovered and question, has it gone through a complete year since it's been discovered? So look that up while I go through this gobbledygook. Again, this is a differential rotating world. 17.24 hours is the rotation period. The weird thing about it is that it's tilted by 90 degrees on its axis, 97 to be exact, which means it spins on its side. Now, how that happened is beyond the scope of this text. I would have to say it got banged by something pretty darn good. It is 4 Earth's diameters, and its mass is about 14.53 Earth masses. So this is not a behemoth. It's large, but it's not that large. Its density is comparable to water at 1.31. So again, that's also Jupiter, by the way. It has a huge escape speed of 21 kilometers per second. And it's about 90% surface gravity. And oh yes, and its albedo is 0.56. So it reflects 56% of the stuff that it gets. Mark you, it does not get very much, on the order of maybe 200 or 300 watts per square meter. But still, it's dumping, it has a lot of reflectivity. So that's why you would see it so bright. Now, I have to admit, on personal experience, the first time I saw Uranus was in 2015. and that was just after I deployed my 6-inch telescope for the first time. I did get a look at Uranus. If we ever get out to Chamberlain Observatory again, or we get to a live night with telescopes, and you get to see Uranus, you will not be terribly Jesus, you will not be terribly impressed. It is basically a blue dot. However, it was kind of cool. At least for me, it was. I'm strange though. Atmosphere composition, as I said, it's hydrogen, helium, methane. There's some ammonia in there. And as I joked, although I was kind of serious at the same time, if you smelled a cat box, a well-used cat box, you've probably smelled Uranus. So that goes down to Neptune. Neptune is the outermost, quote, planet, end quote. At 30.066 AU, its eccentricity is 0.01, which means it's pretty much a perfect circle. It has a 29-degree tilt, so it's comparable to Earth in some ways. It's a little bit outside of the ecliptic. That shouldn't be a huge surprise. It's gotten strange as far as the solar system goes. It's 3.8 Earths and 17.5 Earth masses. Average density is 1.63. So again, we're talking about a planet that is predominantly ices, predominantly water-based, with maybe a few other things, but there's no silicate. The average density, the escape speed is 23.5 again, but they're not entirely sure. It's 1.1 Earth gravities. Albedo again is 0.51. And you'll notice, and this is actually a fault of the place that I took this from, they're calling Neptune and Uranus having about the same temperature of about 55 K, although it will be said that Uranus has, that Neptune and Uranus are both extremely cold enough for hydrogen and helium, for methane to literally be a solid, and or fluid at least. And again, the composition of the atmosphere is here. My big comment on both of these worlds is the strangeness of these worlds is not as interesting as their moons. They are typical giant planets. The other side of the interest for these worlds is many people, some of the new findings of exoplanets out there are predominantly, they used to be Jovian class, and now they're starting to become Neptune class objects. So Neptune, Uranus class objects instead of just Jupiter's. That's just kind of amusing. So they have a lot of mini Neptunes, and with a diameter of 3.8, so that's 4 times the diameter of Earth, and a mass of 17.5. The diameter would almost qualify it as a super Earth, but the mass definitely hints to be something else, and the density also hints at something more interesting. Now, I have to admit that as we've been talking about this, and I've been integrating the exoplanet stuff throughout. As a matter of fact, I work with a couple of people at the University of Arizona on classifying exoplanets, and I've had students do that in the past. But I'd like to, and I'd love to do that with our class, but I don't know. I'm afraid there's not enough time to do that. But they're finding these Neptunes, they're finding these Jovian class planets inside the orbit of Mercury, around the orbit of Venus, and that I'm talking about distance wise. around these other stars. And I have to admit that I scratch my head, because if these are Neptune class, and I'm taking that literally, then some of these planets should not be where they're finding them. It is also conceivable that these planets that they're finding, these Neptunes and super Neptunes and Jovians, are actually migration planets. They're either migrating into their destruction or migrating out to where they will settle down and become dominant of their solar system. This is hard for me to say. This is a research question. If you can answer that, you have your PhD in astronomy from just about any reputable university there is, and you're done. So there's that. The other thing, and I do need to show you this. So I'm actually going to dig into a presentation that I showed you in the past. And this is important for the following senses. Let's see if I have this. Do I have it in here? No, I don't. No, I don't. No, I don't. Okay. So I have to get out of this. So I'm going to get rid of that. Enable editing. Go away. Go. Okay. And I actually want to open up and I'm not trying to wander around or anything of that nature, but I think it's important enough for us to take a look at. Apologies, folks. So I'm going to stop sharing for just a second, go into our Teams and lecture notes. So again, if you want lecture notes and if there's anything missing, let me know and I will be more than happy to put those back up. So, oh yes, let's do it this way. So here is the Jovian notes on the Jovian planets. And this is the picture I wanted you to see. Okay, can anybody, I don't know if you can see this or not, but I am going to make sure that you can, because this is actually kind of important. Let's see. Okay, bring up Teams. And go to Teams. And go to Jovians. And can you all see this? It's the molecular hydrogen, metallic hydrogen, that picture.
Yeah.
Okay. We are talking about these guys right now. These two right here. So 26 and 25. So they're roughly comparable in size to each other. Molecular hydrogen, ice and rock. I almost believe this a little bit more than I would for these two guys, for Jupiter and Saturn. This I can believe. And the reason I can believe that is because you have a lot of ice, you have molecular hydrogen, and even though it is putting pressure on the rock, it shouldn't be enough to disintegrate it. Whereas when I'm looking at these guys, not only are they putting enough pressure, but the temperature should be on the order of 100,000 K, which is enough to turn rock into whatever, sludge, basically. So I'm a little more believing of these two. In the sense that it's basically ice. Now, what kind of ice? It's predominantly, I would say, a mixture of water and methane ice. And I would say that also that there's a bit of ammonia in there and things like that. So it seems to me that it would be something that yeah, there we go. Okay, it would be something that would be very believable. The physics makes sense. So just to let you know how interesting these worlds are, they are actually very interesting. If you did any research on the finding of Uranus, it should have been around 1680 something. And the other question is, has it actually made it to the point where it is where it has gone through a complete cycle since we have seen it? And the answer is, I doubt it. I think it's right now at its equinox. So here we are. This is Uranus. It's nearly featureless. It is nearly featureless because of the fact that it is in its winter, and a lot of the energy for generating weather and all of these planets, well, in particular these ice giants, generating weather is left up to the sun. There's not a lot of heat coming out of this thing. And if you look now, this is actually shot from the Hubble Space Telescope. There is some indication that you're beginning to see storms at the northern hemisphere, and you're actually starting to see cloud bands. And that is indicative of the fact that we're at an equinox. I believe it would be spring equinox for Uranus. So here is the something that we were talking about way back. We were talking about orbital inclination in terms of how it affects the seasons. So in the case of the Earth, as you saw, we have summer in the northern hemisphere, winter in the southern hemisphere, because the tilt of the axis is causing the face of the Earth to face the sun more directly, and we're getting direct light. In the case of Uranus, we see summer at the North Pole, winter at the South Pole. So, and again, we're talking about, if we break this up into 84 years into 4 seasons, we're talking about 21 years per season. So if we start at northern autumn, southern spring, then it's another 21 years, 21 of our years, to go from northern autumn, southern spring to summer at the South Pole, winter at the North Pole. And then another 21 years, so it breaks up to 21 years apiece for each of these cycles. Now, for those of you who are on the North Pole during summer at the South Pole, you've got 21 years of darkness ahead of you. So it's really kind of bizarre. If we look at Neptune, Neptune was a little bit more interesting because we passed that in 86, and it was already in its past its equinox. So here you're actually seeing storms, including what is called the Great Dark Spot. Again, that's a weather low that is causing the atmosphere to shrink down, to flow downward. So here are some cumulus clouds, and again, the serious clouds over Neptune are basically ammonia and methane ice. Okay, so again, we see the same structure pattern of light blue zones and dark blue belts that we saw when we were looking at Jupiter's atmosphere. And again, when Uranus is passing its summer on the South Pole, the North Pole is pretty much dark, so you don't get a lot of energy. You get more energy at the southern pole. This is a structure for Uranus and Neptune. Liquid hydrogen, helium, probably compressed liquid water and ammonia, and a rocky core. I almost believe that. Like I said, I think it's highly more probable than it is with Jupiter and Saturn. Now, if we look at the scale for just a second, and I'm going to grab a ruler and measure it on my screen. Okay. So I am looking at a radius of about let's see, I'm sorry, I did this wrong. 10,000 centimeters, 10,000 kilometers is 2.6 centimeters. Okay, so 10,000 kilometers equals 2.6 centimeters. I'm just going to write this down because I forget things very easily. Km equals divided by 2.6 centimeters. This boils down to 38.46 kilometers per centimeter, or let's call it 4,000 kilometers per centimeters. Okay, so there. What's the point of this? Well, I am measuring 2.3 as a radius for Uranus's core, 2.3 centimeters. Sorry, I have a yappy dog in the yard. 88.46. So I get a core of Uranus of 88.46 kilometers. For Neptune, that's the radius of the core. I get 2.9 centimeters. So I get 11.153 kilometers. So these are the radii of the core. Of the cores for Uranus and Neptune. Let's do a mark. So this one, and that's going from here to the edge. And this one, again, out here to the edge, I get, whoops, darn it. I get 111.53 km. Okay. Eubing, what's your point? Eubing's point is that if we look at the radii of the cores, this guy here, almost comparable to 1, maybe a little bit more than 1. It is a bit more than 1 Earth radii. I get 1.38 Earth radii here for Uranus. and I get 1.74 for Neptune. The upshot is that the cores are essentially the size of the Earth, maybe a bit bigger, but they're still about the size of the Earth. So somewhere around here, these planets were able to gather a huge amount of hydrogen, helium, and other junk. The other thing is that as far as rotation and things of that nature, it's again a magnetic field problem, because we can't really tell what's going on. The clouds are too featureless, maybe not so much in Neptune, but definitely as far as Uranus goes. Uranus's magnetic field is weird, because here is the axis of rotation in pink, and that's this. And here is the magnetic field. And by the way, the axis of the rotation of Uranus's moons is also this way, going towards the rotation axis. Neptune is even stranger, because it has one piece that is not orbiting the way it should. All of these moons should be orbiting prograde, but one is orbiting retrograde, which is very odd indeed. So here is the what we were able to see as far as the rings of Uranus goes, and this was actually done through an occultation when Uranus actually passed in front of a star. We were actually able to make a measurement of the diameter of the ring's width through a photometer, measuring the light from that star as it gets broken up by these rings. So this is a demonstration of that. So when we're looking at the features of these, and I'm going to probably leave this particular presentation in just a minute because I want to get to the KBOs. This is a summary of what's what. And again, I would cast serious doubt on this one and this one. But I do believe these two. Okay, and I think this is the big deal as far as what you're thinking about if you want to keep things in mind for the test, or you're working on your study guides, which you should be doing. Primarily hydrogen, helium, some methane, and hydrogen, helium, and some methane. That's the atmosphere, the magnetic field. They give you roughly the values of those magnetic fields for each of the planets. So again, just comparing size and things for the what this looks like. Now, one other thing, I'm going to get out of this, and I'm going to take a look at the moons. Now, we don't have a lot of pictures of any of them, and that is because we have no spacecraft that has actually explored the Uranian or the Neptunian systems. Voyager 2 made a flyby of each system, took what pictures it could, and moved on. And now, but do we need to know about these? Actually, I would say yes. And the reason I would say this is because of the simple fact that these moons are very, very primitive. These are captured objects from early times of the solar system. It'll give us an idea of what these planetesimals looked like prior to actually getting to the point where they became planets. The same will be said, why do we have this going on? So when we look at the rotation, the orbit of the satellites orbiting around Uranus, weird, even weirder, because the axis of rotation is going this way. The orbits of all of these darn satellites of Uranus are also going that way. So when Uranus had its event that knocked it on its side, so to speak, it knocked the entire system on its side, not just the planet itself. That's very odd indeed. That's very, very strange. So we've got some very strange business going on with Uranus. I mean, there are some interesting things that we may want to know about as far as dynamics goes. Why? If we have a trans-Uranus slash Neptune class planet orbiting another star, what is possible to knock that planet over? Have we gotten to the planet before its actually foundation is complete? That could lead to some very tragic results if formation has not been completed. So these are things we want to know. Here's another shot of Uranus and its four major moons, Miranda, Puck, Ariel, Umbriel, and Titania. This is a shot of Miranda taken by Voyager 2 over the course. Now, if you look at this and compare it with what you were doing in the lab this weekend, since you've been listening to me talk all this time, we're going to take 5 minutes. And what I want you to do is I want you to stare at that picture and then stare at your lab. And in particular, when you were staring at Enceladus, Rhea, Dione, and Mnemosyne. How are they similar? How are they different? Okay, so I'll give you about 5 minutes to do that, and then we'll have a little talk and tell. Hey, folks. Okay, so what are your thoughts on this? It's got to be a lot better picture than what we had in the lab. True?
Yeah. Mm.
The only problem I have is that I can't really zoom in. But there's a couple of things. Okay, go ahead. Why don't you guys tell me what you're thinking, and then I'll share my thoughts with you too.
Is there any errors with the pictures? Like,
Say again.
is there any mistakes with the pictures?
No,
No? Okay.
no.
Um, so I was looking at like the streaks of lines it has on the sides, and it kind of looks like fault lines, maybe, if I'm not mistaken. And
Yeah.
then I'm looking at the clusters of craters too, and it's like, well, and I was trying to determine like whether it's active or not, and I honestly can't tell.
Because you have up here, let's see if my pen, you have up here these craters up here. So there's a lot, there's a couple clusters there. There's a cluster here, I think. And I can't see the other side. There's some more stuff here. But then you get this stuff.
Yeah.
It's kind of fun being a planetary geologist, or at least staring at some of these pictures. I can't tell if this is this looks more like a fault, like some crinkles in the surface here, going this way and then going this way. So with this thing, and maybe we can figure out something with this. We'll explore this in just a moment. I want to show you something weirder. This is Miranda, that's the moon of Uranus. So now here is the surface of Triton. And again, what we see is cantaloupe style terrain, as the text says right here. And I can't really tell from the picture if there's an atmosphere there or not. They say there is, but I'm not, I never take anything that they say at face value. I am going to take a screenshot of this. And I have the ability, I love the fact that there's a program, if you ever want to get into screenshots and stuff like that, called Snagit. It's like $20 for students. I think that's right. So I've taken a screenshot of Triton. And this Triton is actually a moon that is roughly the size of Pluto, but it's going retrograde in its orbit around Neptune, and it's actually going to spiral in. So I'm going to go backwards to one slide, and I am going to take another screenshot of this. There we go. Okay, so okay, and let me go ahead and here. And I am going to escape this show for a moment. And I'm going to discard those changes because I don't want to save them. So now you're actually looking at a Juno picture of Jupiter. And if you if you're ever feeling bored on Facebook, tired of hearing about COVID-19 and the other nonsense, then take a look at JunoCam on Facebook. You can actually suggest places that you want to photograph on Facebook, and it'll be sent to the mission directors of Juno for future considerations. Look at the wild colors and spirals that you see on Jupiter's surface. I didn't want to show you that. What I wanted to show you, I am actually going to bring up our friend, the solar system guide. And I did make a couple of movies this weekend regarding looking at the different cosmographia versus this. This is exactly cosmographia. And you can download cosmographia and have it forevermore if you want it. But what I'm going to do is I want to look at explorations, and let's see. So March 13th, 1781 is when Uranus was discovered. So that's 239 years ago. So it's almost on its third trip around the sun for us. And now I'm going to go to moons, and in particular, let's take a look at Miranda if we can. There's Ariel. And here again is some interesting features. Look at the highlands and the crinkles that are going on this moon. Yeah, you have your craters like the moon, like our moon, and like Ganymede, but you also have these crinkles here that are very, very difficult to understand. Here is our 3D model. Something I love about this. And this is all the pictures we have of Ariel. So if I were interested in finding out more, then my question would be, and one of the things I'll try and leave you with is the idea of where could I go for further research? First of all, looking at this, I've got these things here, which are just weird. This is Ariel, by the way. We'll get to Miranda in a moment. So these are the best pictures we have of Ariel. And let's see if I can get it to zoom in. I might be able to. There we go. Look at this. And then here too. This, where have you seen this before?
It's one of Saturn's moons. I forgot how to pronounce the name. Starts with E.
Iapetus? Oh no, no, Enceladus.
I think so. Yeah.
Yeah. Where else have you seen this before?
Well, it looks to me like a river. Like,
Yeah, it does, doesn't it?
mm-hmm.
And there's another place we could go to see something like that. And let me take you there. I'll take you there. Let's see. This is gonna, in my opinion, I know that the school has a particular way that you're supposed to teach astronomy. I'm, but I think this will revolutionize things a little bit. But let me take you here. Come on, chop chop. There we go. There we go. Doesn't that look familiar? Oh, I can't zoom. Hang on. I'll find something that can zoom. I know I'll find something that'll zoom. Oh, come on. You had this. I know I saw it. Core. Ooh. Look at that. Huh. Global elevation, topography, surface roughness. There's our friend Mars. And that darn well does look awfully familiar, doesn't it? Thermal inertia. That's a hot spot by the looks of it. And that's awfully cold right there. Temperature change, more. Okay. So you can actually read up on this, and I'll leave that as an exercise to you. I think it's an exploration that you can find that that 3D model. I know the next time I teach this, I am going to learn how to 3D print, and I am going to print these things off so you guys can handle them. Or maybe I'll make an assignment for you guys. Shoot, I can't. Oh, there it is. There it is. I knew it was. They had it one because that is Valley Marineris. When I look at that, let's pull, go to full. Where the heck did it go? Oh, there it is. Never mind. So when we look at Valley Marineris, this is what we see on Mars. We looked at Ariel, that looks the same. There's another good shot, actually. That's probably the best shot I can think of. I'm going to save that. Because I think having those around is probably a good thing to have. Bum, 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 bum. So if you have access to a 3D printer, and I don't know if you do or not, you probably don't, I don't know. But you might want to consider a 3D print of this. That'd be kind of cool, honestly. I know I'm going to do that when I get next time before I start this class again, that I would 3D print some of these things because it makes it so much easier to figure out what the heck is going on. There's Oberon, and Oberon is a very weird little planet, planetoid of itself. It looks more like it's a dead world. And these are all the shots that we have of it from Voyager 2. And they're not great resolutions. Voyager 2 was a great little spacecraft, is a great little spacecraft, excuse me. But it is, the technology is kind of old. Umbriel, Titania, Puck, Oh, there's Puck. That's so pixelated. But something else I wanted to show you. Let me get back to Miranda. Let me focus on what I'm supposed to be doing. See if I can find that. Miranda. So there's Miranda, and there's a close-up of those ridges that you were talking about, Jose. And if we were to look at this, and here's the model that we have, and you can see that a good portion of it has not been mapped. I mean, we get these nice shots because they actually mapped them from spacecraft images. And here again, this is Voyager 2, so it's really old technology. But here again is very much like Valles Marineris, isn't it?
And what are these ridges?
These are ridges. Well, that almost looks like Valles Marineris, and I don't know what they named it. But here again, you have these ridges here, and that's another weird part of this whole business.
What are they caused by?
Well, that's an interesting question. If you were to think about what causes our ridges,
Like tectonic plates and
yeah, some kind of bumping around. Although tectonism doesn't seem to be, when I look at this moon, tectonism could be in the form of heating and cooling. So what would be interesting to find out is density. I would be intrigued to find out what the density of this moon is. And I don't know if they have it on there. And if you find it, let me know. But when I look at this, I start thinking of density. Look at some of these craters here. Now I'm going to show you somebody else. And you may find me very weird for this, but that's okay. I am weird. So I'm going to go into Kuiper Belt objects. And something I want you to see. Yes. This is the first thing I want you to see. This is Pluto. Most notably, this is Pluto's atmosphere. So when they start saying, "Oh, Pluto's not a planet," really? No, that's not what I wanted. Here's what I want. Here's another shot of geologic activity here. And you can see the haze where the atmosphere is ending. It has a very thin atmosphere. This is the natural color of Pluto. And I don't know if I can open this. I was actually going to throw that in to a presentation. Here's another shot of the frozen plains. This is Sputnik Planitia on Pluto. And you'll notice that there's a mountain range right here. And don't worry, you're gonna get to see a full shot of it. I would not deny you that. So here's what we have of Pluto. And Sputnik Planitia is a very, look at this on the right hand side. So we're going live now. This is a close-up of Sputnik Planitia. And I call your attention to it because of the cantaloupe skin that you saw on Ariel, and some of the riffs and such on Miranda. So I think that's part of the reason, and I'm calling your attention to this. This is again another shot of this is Sputnik Planitia here, and these are the foothills. Okay, and mark you, this was taken from, let's make sure that I'm saying it right. Oops, that page is not found. It's weird. Let's get a good global map. And I think featured images are worth the time to take a look at. Oh, I got to do that still. Okay, so no, I haven't finished with Pluto even as we speak. Does this when I'm bringing up this whole Miranda thing, excuse me, and I just I'll bring up the picture that I saved, and actually let me copy, and I will paste it to Teams for your viewing pleasure. So here's my shot of Miranda, and let me get one other shot to you guys before I move on. I'm sorry for the nonlinearity, folks. It's just that there are some things that are best, well, I don't know if it's best done live, but hopefully this is making some kind of sense. So here are the pictures we were talking about of Triton and of Miranda. And let me now go into Pluto's images. The basics. So here's Pluto Charon facts, 39.482, let's call it 40 AUs from the sun. 248 years. It was discovered in 1930, so it hasn't gone around once. The temperatures range from, can you see this okay? Can you guys see this? That I'm looking at New Horizons?
Yeah.
Okay, that's the website, right? You're seeing my Chrome.
Yeah.
Surface temperature 396 to minus 396 to minus 360 Fahrenheit. Let's see. Abigail, you are definitely going to have to wear a jacket. So are you, Lucia? Because that place is cold. Mass is roughly maybe 5% of the Earth, if that. Density is 1.8 to 2.1. So here again, we're talking water or ice. Density of Charon, which we have exact measurements for, is 1.6 grams per cc. Surface is pretty much frozen water, nitrogen, methane, carbon monoxide. Surface of Charon is basically water, ice, and ammonia. Atmosphere on Pluto is nitrogen, methane, carbon monoxide, and atmosphere on Charon is nothing. The spin period, these are actually called a binary planet because Pluto and Charon are not considered planet moon, they're actually considered planet planet. The orbital period of Charon is 6.39 days. I want to show you the gallery. Surface composition. So this is Sharon. And actually, let me get back to the Solar System Explorer. Let's do this right. So there's another shot of the surface of Pluto. Here is the quote-unquote heart of Pluto, which is called, also known as Sputnik Planitia. And we'll take a look at that in just a few moments. I'd like to get into that 3D model if I can. And here's another shot of Sputnik Planitia and the foothills thereof. And I think they're called Cthulhu Heights, but I think that's right. After the creature from Lovecraft. Okay, so let me see if I can find this. I really, hopefully they did it. Okay. Here's the core. It has solidified. Nitrogen atmosphere, water, ocean. And they're pretty sure of that. Here is the thermogram. Showing the different temperatures, elevation map of Pluto. This is what we got. Oh, I can't zoom in. Darn it. So this is the shot that they got as the spacecraft was flying by. And I really want to get to that 3D if I can find it. There's another shot of Pluto in real time. Ah, here we go. That's what I want. So here is what we have. We have Pluto from a point of view that it has mountaintops here. And you see crater clusters here. And then you look at this, and it's all cracky and crinkly. So that is very, very odd. And let's see if I can get more of what they got. Nope, that's it. Okay, so we look at this area, and again, we get cluster craters, but they're not as deep. They're almost comparable to Ganymede. And then you have, again, these weird ridges. Kind of very much like what we had before. I am going to try and see if I can't take a screenshot. I'm going to animate it too. Hang on just a second. Webcam off, record microphone off, preview and editor, record system audio on. Okay, so I'm gonna make a movie of this and then throw it into Teams. Come on, you can do it. You can do it, you can do it, you can do it, you can do it. Okay, here we go. All right, I hope you don't mind. It is not recording your voices, by the way. It is not recording system. It is recording system audio, so, but it's not. And let me shut that off, as a matter of fact. So you can see that I'm just taking a screenshot. I'm going to leave the audio off for the time being. And let's let this guy go. And I'm just going to let Pluto rotate a little bit. Okay. I don't even want to imagine what these things are. This image right here, by the way, can you hear me?
Yes.
Yeah.
Okay. These are basically from the Hubble Space Telescope. So any of this hazy stuff right over here is Hubble. The stuff that's coming up on the limb here is the stuff that New Horizons took. So this is where we want to zoom. Look at this. That's cantaloupe skin if ever I saw it. And then there's this. And I'm going to pull it back for a second because there's one place that I would suggest you take a look at on the web, on your own time, if you will. And that is Antarctica, the Antarctica ice sheets. Because my money says that that looks exactly the same as if it's ice cracking or ice formations. So Pluto is active. I should tell you that. It does have an atmosphere. And it would be very, very cool if we could send another spacecraft. Of course, it took 10 years to get there, to take a look at some of these features here. That would be pretty wild, in my opinion. Maybe send a Pluto orbiter. Because when you look at Pluto, it's not like it's going to generate light, as far as I know. Mark you. But it might have some a place where you could possibly put some life on it. So I've finished my video, and I am going to not edit it. I'm just going to go ahead and copy it. Oh, I can't, I guess. Okay, save. Okay. And I'm going to throw that into the desktop so that we have it. And let me now do a more structured attack. Oh, God grief. Is everybody okay?
Yeah.
Have I generated confusion?
Well, no, I don't think so.
Oh, that's good, because frankly, I found that whole thing very confusing myself. The whole situation with Pluto was very confusing, very exciting, I might add, because I watched quite a bit of it, believe it or not, on Facebook. You know, I'm not a big Facebook fan, but, you know, when it can be useful, it is very useful. Okay, so let me do this last thing, and then I'm going to show you a couple of things, and then we'll stop. Here. Okay, so now I am going to paste this movie into Teams so that you guys can get it and take a look at it. Edit. Oh, for heaven's sakes. Copy. And let me get to Teams. Just remember, if you have anybody to blame, just blame Natalie. Okay. Paste. No? Okay. or Abigail.
Hmm.
Okay, it's not letting me do that, so I'm gonna have to go drastic, and let me see if I can find this thing. Show in. Okay, 504. So let me do this. All right, so let me just throw a couple things at you so that we're on task. So this is called Asteroids, Comets, and KBOs. This should be available in the Teams, and I will put it in D2L as well so that you all have it. There is a mission going on right now called the Cirrus-Rex, and the idea of the mission is to go to an asteroid, the asteroid Bennu, recover a sample of that asteroid, and then return it to Earth for analysis. So that's going on, that is ongoing. And there's a movie about that in this presentation. I'm going to skip it for the moment. So another mission of interest is the Dawn mission. By the numbers, this mission just ended, by the way. 51,000 hours of flight. It went to 2 asteroids. It went to Vesta, and then it went to Ceres. And Vesta was kind of, it's okay. But Ceres was something else. And I was following that. Actually, I went to 3 talks at U of A on that because one of the lead investigators for the Dawn mission was at the University of Arizona. So the Dusk for Dawn, this is the mission. This is a summary of the mission, the Dawn mission, to the 2 asteroids, and I'll just leave that for later. And I think I'll just leave that go. But here's the 4 largest asteroids. Ceres at 939 kilometers, Vesta at 525, Pallas at 512, and Hygiena at 434. Notice that, and let me just get a pen, that Vesta is basically a potato. So here's a comparison of Vesta Ceres. So this is Vesta. It looks like a potato, like a very big potato. Here is Ceres, which is very weird. And here's our moon. So again, you know, when I was first taking the subject of astronomy, it was predominantly, oh, there's only water on Earth. Oh, hell no. It's on the moon, it's on Mars, it's on Europa, on Enceladus. Pluto has water underneath the icy surface. I would suspect that Miranda also has it. It'd be very interesting to see what that moon's density is, like I said. And more importantly, so does Ceres. Okay, these bright spots right here are indicative of water. So the TNOs, otherwise known as the KBOs, the Kuiper Belt objects, as they're called, we have Eris and Diacenema. These are the outermost planets, or dwarf planets. We have Pluto, which has 3 moons and is a binary with the object Charon. Mahi Mahi, which we have absolutely no idea about. Hanomea and Helicaya, okay, whatever, and Nemekia. These guys, if you look at them, remember I said that undifferentiated planets are potatoes. I need not say more. There's Scelacea, 2002 MS4, Vanith and Oculus, Sedna, and Quaoar and Waiwalt. Okay, this is an image from 2015. So most of the Kuiper Belt objects actually have companions, and there are more being discovered all the time. These are way, way out. We're talking Pluto is 40 astronomical units out. Eris is almost 80. Oh, here's Pluto and Pluto Charon. I think I showed you that from the website. I took a picture of it and decided to throw that in with the Pluto Charon system because the Pluto Charon system is a damn interesting system. It has a lot going on. This is what I mean by what is called a binary planet. So if I look at the left-hand picture here, we're actually not seeing Charon orbiting Pluto, but rather Pluto and Charon orbiting a common point, which would be probably about there. And the picture on the right is actually a shot on the right-hand side where you're actually looking at the oscillations of Pluto as it goes from a side view. So this is what it would look like. Why do we care about that? We care about that because if we're going to, as our technology for exoplanet discovery gets better, we're going to be able to see something like this happening with planets that we discover. It's only a matter of time. So Pluto at a glance, this is all the data. The big deal is the heart of Pluto here, which is predominantly waterway. And if you start looking and comparing this to the Lake Liga Mare on Titan, it's kind of the same thing, except this one's frozen. That one on Titan is liquid methane. So here, out here, where the temperatures are as cold as they are, methane is not going to be in a liquid form for very long. So here's Splonica. This is a side view, and the dunes of Pluto are some of the more interesting facets. Now, mark you that this is about 3,000 km by 6,000 km. Okay, so we could probably with, and I'm not going to do it right now because frankly, I don't have 100% scale. If I were to get a scale though, we're talking these hills here. The estimate is about 8,000 feet high. So here's the spectra of Pluto, which I think is important from the following perspective. You guys remember what I said about the whole idea of spectra. We can't bring Pluto in and cut a piece of it off and say, hey, here's what we got. No, we have to do spectroscopy. So when we do spectroscopy, we see all the lines that are associated with methane. And once again, we're starting to look at when we got the surprise of our lives, maybe not that much of a surprise, coming from the atmosphere of Pluto, that it actually does have an atmosphere, and that that atmosphere, we believe, hypothetically meaning, comes and goes. So when, yeah, hang on just a minute. Hi, folks, sorry. Okay, so I'm just going to make some final remarks on the atmosphere. Predominantly methane, with water vapor and nitrogen as well. So here's the thing with Pluto. It's a living world because it's not exactly, let me see if I can advance the slide. Okay, there we go. So this is what we think. It has a nitrogen atmosphere. We have ice cooled by sublimation. And we think that the atmosphere is coming up from the melting of the ice as Pluto nears its solstice. Okay, I'm going to end here. I have a couple of things that I have to take care of. Are there any questions? Are we okay?
Yeah.
Let me get out of this. Okay, so we have another meeting. I have office hours tomorrow. Let's see, I have office hours tomorrow, and then we have another meeting on Wednesday. In the meantime, let me just get this set up. Okay, so I am going to post that stuff into D2L, or not D2L, to upload from my computer. Let me find that silly thing. Desktop. Okay, so here is the Pluto video. And that should take, it's going to take a few minutes to upload. And in the meantime, we will talk on Tuesday, Wednesday. Don't make me work during office hours. Come and ask questions, okay?
Okay.
Okay.
All right. Have a good rest of your day, and I'll see you all tomorrow and Wednesday.
Bye.